Okay, so this is okay, so that's a theorem that we have already used, and I just mentioned it. But this one refers to homogeneous equations. So in other words, b is equal to 0. Okay, so I did not provide any evidence in support of this theorem, so I think maybe I'll just mention this picture. We'll go in and use this picture for illustration. This one, it is a very nice picture, and it comes from the algebra that precedes it. As you can see, a system of equations converted to an augmented matrix. So it's this one, augmented matrix on the right, and the matrix equation. No, there is no matrix equation here, actually. Just the, I suppose, I'm not sure what, there is no special name for that equation on the, not the top is the augmented matrix, the system of equations on the left, the two versions of it, and there's no name for that one. I don't think it is. Like, I suppose maybe it's, be fair to call it the vector equation. There is no matrix, right? Vector equation, the system, the original system. So if you want names for everything, this is the system. The system, augmented matrix. Okay, the vector equation, one equation, and, well, that's it. Okay, so these are three, and the matrix equation somehow is not here, but I could just as well write it here, just for reference and for review. Matrix equation from what we've got. Let me take the original, so it will be 1, 0, 1, 1, 0, 1, 2, 1, multiplied by x1, x2, x3, x4, and it is equal to 1, 2. A little bit doesn't fit. And the answer is 1, 2. Okay, so so you see this matrix equation that how it works out. So 4 different names for pretty much the same thing, right? Original equation. In what order? I would say number 1, the system itself. Number 2 is the vector equation. Okay, then it is actually quite important. We're gonna talk about that. Number 3 is the matrix equation, and the number 4 is the augmented matrix, is the abbreviation of the matrix equation. Okay, so this is supposed to be 3. Okay, so as I was talking about, what happens if our system is homogeneous? So we have then S is equal to 0. So this one, S is equal to 0, so this would be gone. Okay, what difference does it make? Look at what happens. We need to produce one non-zero solution. That's what the theorem about homogeneous systems speaks. And so how do we do it? I simply pick t equal to 1 and s equal to 1. S equal to 1. So as you can see, the picture on the left are those two vectors called u and v, like this. They are at the tip of vector s, which we now decided to be 0. Okay, so which means that both vector v and u start at the origin. Okay, but otherwise they are just like this, still separate, and they are not multiples of each other, which is by design. Well, why they cannot be multiples of each other? Because the augmented matrix will have, which we coming from, will have zeros over there. Where is my augmented matrix? It is. It is not because the augmented matrix is in the reduced row echelon form. So that is the reduced row echelon form is here, is visible here, and which means that x3, x4 are the free variables, and they're expressed in terms of each other and nobody else. And as you can see, if you if you try to vary t and s, what's going to happen? They cannot cancel each other as long as t and s not both equal to 0. These two vectors cannot add up to 0 because of those two last entries, right? One vector has one entry in that place, and the other one is 0, and vice versa, which means that whenever you try to take multiples of those, they will still have non-zero entry, either one or the other or both. Okay, so that is the nature of the picture that we see when we start varying the two multiple of u, that orange line, multiples of v, the green line. Okay, and then we try to add them together. As you can see, they will never add up to 0. Okay, so that's why we create a whole plane. To demonstrate that there is at least one non-zero solution is really easy. As I pointed out, you just take t equal to 1 and s equal to 1. They cannot possibly cancel each other, and so we right away have a solution which is non-zero. Okay, but other than that, as I mentioned earlier this week, this is how we produce more and more copies of the Euclidean spaces. But this time they are not necessarily created by forming a Cartesian system, but rather they come from vectors, and as long as these two vectors u and v are there, as long as they are not multiples of each other, they do not have to be perpendicular. But as long as they are not multiples of each other, which means that they are not parallel, okay, as long as they are off, there is an angle between them, they will create in that manner. Remember, this is called a linear combination. Will produce a whole plane. Okay, so that's how we create. That's how we create planes. They don't have to be necessarily like xy plane with two perpendicular axes. Okay, so all right, so that was just a reminder. Now, Gaussian elimination is what we're talking about. So that is something that I want to wrap up. Okay, what happened here? Okay. So the plan is to do first row echelon form, zero staircase, okay, and then zero staircase with leading ones, and then use those leading ones to eliminate entries above them. Okay, so that's missing here, and that is called the reduced row echelon form. Okay, so so this is how we do it in a manner that is recursive. Okay, so we start with a matrix and make sure that in the first row over here we have a non-zero entry. Okay, so step one, make sure that entry, which is non-zero. Well, first of all, if you do have a 0, then what do? You either do interchange rows, or if that fails, interchange columns. Right, so you always can have, sooner or later you will get one non-zero entry in that location. Okay, once you do, then you divide by that value, divide the whole row by that value. So in other words, I don't know, whatever, if it is c not equal to 0, then you put 1 over cr1 as the first row, and then you have a leading one. Okay, so that's the minor step. And then you have a whole cycle over here. This is a cycle that you're going through all the entries in that column, in the first column, and eliminating one by one. Okay, so it's probably worthwhile what it means. What does it mean to eliminate non-zero entry with a leading one in formal language? So it is if I have 1 here and some whatever stuff elsewhere, and then I have a non-zero entry here, say z. I don't like z. Okay, fine, c. Okay, so what do I do? Say this is R1 and this is R2. It means replace R2 with what? With a certain combination of R1 and R2, which would make c equal to 0. So replace R2 with CR1, well, R2 minus CR1. Okay? So then the result will be nothing happens to the first row. It's still 1 star star, and the second one becomes 0 and some numbers elsewhere. Okay, so that's the tool that is being used throughout this operation. And so once again, eliminating non-zero entries below and above a leading one. Okay, so so as you can see, then so stage 1 is to in stage 1 we eliminate step 1 rather, we make it first a non-zero entry, then we make it a leading one, then using leading one to eliminate all the entries below it, and then once we're done, then we reduce the size of our matrix like this. So we remove first row and first column from the matrix, because we're not going to be using the first row. It's our choice, and we don't need it. And then even though the rows below will be used, and they do have the entries in the first column, but it doesn't matter, because whatever we do from what's left, all of these zeros, they don't matter, because 0 plus 0 will always give you a 0. Okay, so that's why we justified, and we are ending up with a smaller matrix by 1. Okay, so it is by the way, very convenient to sometimes if you have too few rows, you might add rows made of zeros in order to accommodate to make it a square matrix. It's sometimes just sometimes helps. Okay, so and then you repeat this process, which is once again find non-zero entry, turn it into 0, 1, eliminate entries underneath. Okay, and then you have a new smaller matrix yet. Okay, and then on, and then repeat it as many times as necessary. So this is my cycle, like this. And so smaller matrix, and then you end up with a bunch of leading ones. And not only you have a row echelon form, the way we have discussed it is a slightly more convenient row echelon form. It is the staircase is not exactly one step at a time. So you are descending directly one step, 1 row per column. Yeah, 1 row per column. Yeah, so diagonally you're descending. So that's what you're going to end up with at the end of stage 2, stage 1. Okay, and then stage 2 is very similar. They're similar, except the cycle goes in the opposite direction, and you're going from right to left, from right to left. So cycle is from right to left. From right to left, and you could go up and down and up, and that doesn't really matter. Just as here, I put an arrows here that going down, but that doesn't make any difference whatsoever. You can go just as well up. The order of these rows doesn't matter, as long as you progress from left to right. Now that's important, that you have to progress from right to left. Well, as it is described. So the plan over here is just a general description, and we just have and then below we turn it into a more precise algorithm. And here you go from right to left, indeed, so that you would not have to recycle your you wouldn't ruin your zeros. That's the trouble. Why the order matters? It is there's a chance that you simply might use the row with a 0 somewhere, and then those zeros stop being zeros anymore because of the algebra that you carry out. Let me just do an example, and I think it will be just easier to see if I illustrate this. Okay, so as an example, so I'll just start with a matrix right away. So I have, say, 2, 4, 6, 8. Let me do homogeneous. So I'm dropping the last column to make my life easier. 1, -1, 0. Okay. 1, 0, 0. 2, 0, 0, 1, 1, 1, something like this. Okay, suppose this is my matrix. The top left entry is non-zero, so that is satisfied right away. But I want a leading one, so what do? I replace the first row with 1/2, with half. Okay, so it's one of the elementary row operations. The result is 1, 2, 3, 4. And now I do nothing with the rest, so that is some amount of copying is inevitable. Okay, and now I do a cycle. So this is my matrix now. I'm using the leading one, and I'm supposed to eliminate these. Okay, so how do I eliminate these? As we know, I just simply replace R1, R2 with R2 is replaced with R1 minus R2, right? So I keep R1 intact, and I simply subtract the second from the first, or second. Yeah, it's easier. First minus second. So it will be then 1, 2, 3, 4. 0, 1, 3, 4. And now, okay, so, okay, I got 1, 0 in the first column, as planned. Now moving on to this, the third row. So how do I eliminate it? I simply add these together, R1 plus R3. So I replace R3 with that. Okay, and so what do I get? I get 0, I get 4, I get 3 and 4. Now the last row we get for free. 0, 1, 1, 1. Okay? So 0, 1, 1, 1, that's my new matrix. And now we continue with the cycle, moving right to left. But more precisely, I just I do this. So I'll just take a small matrix. So more compact. It's more compact, so I'm getting then 1, 3, 4, 4, 3, 4, 1, 1, 1. That's my new smaller matrix. I already have a leading one, so I'm going to be using it to eliminate those two entries underneath. So how? The same way. So I'm keeping the first row intact, 1, 3, 4, and then I multiply the first row by 4 and subtract the second. So right, so I multiply by 4. So you can do it in your head, and sometimes actually it's easy to make a mistake. It's a very easy operation. Multiply the first row by 4 and then subtract, but if you do it in your head, it is possible to make a mistake, unfortunately. So just watch out and make sure that it don't make a mistake. So 4 minus 4 is 0, okay. 4 times 3 minus 3, is it? I think it is 9. Right? Yeah. Okay. 4 times 4, 16 minus 4, 12. Okay, great. 12. Okay. And then now I need one more. So what's the next step? Yeah. What?
Subtract R3 from R1.
Yeah. Okay. R3 minus R3. So 1 minus 1 is 0. 3 minus 1 is 2, 4 minus 1 is 3. So that is my new matrix. So I have another 0 column, and so I'm expanding my staircase. This is my new matrix. It is small. Okay. Okay, so let me just take a record of it. So I have 9, 12, 2, 3. Okay, and now I have a non-zero entry, but I need to make it 1. Once again, maybe there are easier shortcuts, but that's for a person. If you were thinking about an algorithm, well, let's try not to be too smart, and let's just go straightforward as planned. So I will typically divide by 9. Okay, so 1/9 R1. okay, which gives me 1, and 12 divided by 9 is
4/3.
4/3. 4/3, and well, and then that's it so far. Okay, but that's good. So now I have my leading 1, and I am to eliminate this 2. Okay, so I go on to just multiply the first by 2. I keep R1, and then I multiply 2R1 minus R2, and what do I get? I have 1/4. I have 0, and now I multiply 4/3 by 2, which gives me 8/3. Okay, 8/3 minus 3. Oh my, 8/3 minus 3, I think. Negative 1/3? Yeah, negative 1/3. Negative 1/3. Okay, so I have a row echelon form. Let me put it together. Okay. So I'm reassembling my bigger matrix from these. So I could start from the right, bottom right. 1/4, 0, negative 1/3. Okay, but there are 4 rows and 4 columns of zeros by design. These are zeros, right? And then let's see what we have eliminated initially. We just have to look at the first and second rows. The first row is still visible right there at the top, are 1. The top, so 1, 2, 3, 4. 1, 2, 3, 4. And then underneath this is 0 naturally. And then what we eliminated from over here is 1, 3, 4. I'm sorry, I actually said that it is a row echelon form, which is well, it is a row echelon form, but we're going to take care of that last element. No, row echelon form requires a 1 there, so sorry about that. I have to have one more step over here in order to have 1. So it will be 1/4 and 0, 1. Okay, fortunately it's homogeneous system, so there is no danger of ruining. I don't need an extra computation, so I simply have 1 here. It just happens to be, I picked numbers at random. You saw I just was writing in the original matrix, I was just writing numbers at random, and yet we ended up with what? What is so special about the system? What? It is a row echelon form, yes, but can you tell or predict how many solutions it has got?
How many solutions it has what?
It's got.
What?
Solutions meaning 4 numbers. It has 4 unknowns, so 4 numbers. So it's a vector in 4-dimensional space. How many? No, remember the problem. On the test that you can have 0, 1, or infinite. Okay, so is it 0, 1, or infinite?
I think it's 1.
That's right. It is 1, and what is that 1 solution? What? It is 0. It is a homogeneous system, so 0 is always a solution, right? But because of the, look, we ended up with the number of rows equal to the number of columns, and the number of every variable by accident ended up to be a dependent variable, okay, which means that there are no free variables, which means that there is no, you will find only one solution, okay. You can think about, if you just can write it out in terms of equations, you can see that from the last equation I can find x4. Then I plug in x4 into the third, and I find x3. Then those two are plugged into second equation. I'll find x2, and so on. Okay.
So if there's an empty row at the bottom that's all zeros,
yeah.
Does that mean that it has infinite solutions?
I mean, if you are, I mean, you can add free as many. You'd better count the number of equations relative to the number of variables, not just whether there is a row there or not. So in this particular case, if the last row was 0, then yes, we would have infinitely many solutions. And in fact, we would know that it would be a line. The mismatch gives you the dimension, the gap between the number of variables and the number of equations will give you the dimension of your solution set.
Oh, okay.
So if 1 is missing, it's a line. 2 missing, it's a plane. Just that example that we just saw over here, right? Two equations. If you don't count 0 equations, then there are just 2 equations for unknowns, and the end result, as you can see, is a two-dimensional space. Okay, but why did I end up with 4 equations for unknowns? Because it is generic. It's more generic. If you do it at random, you are more likely to end up with this, with the rest. So it's if you have 4 equations for unknowns, then just what to be expected is the generic situation, and the generic situation is one solution. Okay, but you can imagine that you just could have fewer equations or more equations. You don't know ahead of time. And even if you have too many equations, it doesn't mean that you're going to end up with a small solution. They might just start dropping off because they're canceling. You don't know. So that's why we have a general method. So anyway, so what do you do with this? So this is indeed a row echelon form. So by the way, you can notice that we're using a row echelon form, and we're using the reduced row echelon form because row echelon form is not unique. You may, depending on the operations that you choose, you might end up with a different matrix, augmented matrix. But if you do your job right, then the reduced row echelon form is always the same. Okay, so so that's stage 1. Now stage 2. Stage 1. Stage 2. Let's go on to eliminate a few more entries. So I'm going backwards now. So I'm using this leading 1 to eliminate entries above it. Okay. So I keep the last row R1, and so 0 0 0 0 1. And what do? I do it. It's fairly easy. In fact, I don't have to go up. I could go down if it's more convenient. It doesn't matter. So I'll have R1 minus 4 R4, right? So I need 4. I have 4, and then I'll just eliminate everything. You can see how things work out. So what does the first row look like now? 1 2 3 0, right? So as notice that nothing has happened. It was 1 2 3, and then still 1 2 3. And the second row, I will have the same operation. It will be R2 minus 4 R4. Machine. And so I'll have 0 1 3 0. Why? Because the last row has only one entry, not 0. So it will not affect the rest of the entries other than on the very last one. So similarly here I have R3 minus 4/3 R3. And so 0 0 1 0. Okay, so can you predict the end result? What? Identity matrix, right? So I don't want to waste too much time. Indeed, it will be 1 1 1 1. The identity matrix, indeed, 1. Oops. 1. And the rest is zeros. And that proves that indeed there will be only one solution. Because it was a homogeneous system, so what's on the right here, it is Ix is equal to 0. Okay, so after all this work, we have a new equation, matrix equation, except our matrix now has become way simpler, and we ended up with equation Ix equal to 0, and then there's only one such an equation, so such an x, it is 0. Okay, so if you multiply that kind of matrix, it is, well, why? Because Ix is equal to, I'm sorry, I0 is equal to 0, and, well, there are no other options. Come on, what is it doing? It's doing it again. Okay, so we conclude then x equal to 0. Imagine that it was not homogeneous. Then what would have happened, I would have an extra column here. It would not do any difference as far as our decision making is concerned. So whatever we have been doing, we would have been doing it anyway, right? So there will be just more work. But we are eliminating, we're only looking at the leading one every time. We're looking at the leading one and looking at the entries above or below it to kill, okay? So, and the end result will be pretty much the same. We would have had one extra column and nothing else. So then the answer would not be 0, but it would be still a single equation, because when the matrix ultimately is the identity matrix, there can be only one solution. It is when you end up with, as we have in the past, that example we just saw, if it is something like this, well, that's exactly what we just had, right, in that example from some time ago. Well, that would be a two-dimensional, right? So if this is the case, my matrix is this. It is the reduced Rorschach form, but the solution set will be two-dimensional. Depending on the number of 0 rows at the bottom, we're going to have the dimension of that will be the dimension of the space of solutions. I'm using the word space because it refers to it is a copy of the Euclidean space. So this is our R2. The solution set is literally R2. Okay, so there might be some homework after the break of this nature a little bit. I hope the algorithm is clear, and so we're gonna proceed to the next topic, which is where all the stuff is happening. More algebra and more structure of solutions, and primarily, well, one thing to remember. I think I want to say it now. Matrices are functions. Okay, so that would be what the story will be about. I guess we'll just then adjourn right now.